Okay, we have discussed concrete, cement, and steel already, but this is a new article that just came out in February of 2025, a couple of months ago, and it again makes a few points about what the promising methods are now that are emerging to reduce emissions, resource use, and waste from construction industries. Every time you see a tall building being brought down, it generates so much debris, so much mashed up steel and concrete that you don't know what happens to it. No, it gets hauled away and then you don't know. So how can we make concrete sustainable? This is the use of 3D printing to lay down concrete, which can reduce carbon emissions and waste in construction. So when you have to pour, mix in a big cement, what is it called, a mixer, and then you pour it out, and then labor hauls it out and pours it into shapes. But if they are 3D printed, then that whole process is, you can see this pipe here laying concrete in these kind of design that is, it's not very important what the design is, but it's 3D printed so that the system is very automated, and just one person standing there and doing all these things. So cheap, strong, and versatile concrete is the second most consumed material globally after water, with 30 billion tons used annually. Production of concrete is energy intensive and is responsible for more than 7% of the anthropogenic carbon dioxide emissions, of which cement accounts for the vast majority. We discussed that already. Extraction of the minerals and other materials used to make concrete is also environmentally unfriendly. For example, around 50 billion tons of sand and gravel and more than 5 billion tons of limestone are mined annually, resulting in habitat loss, soil erosion, and pollution. These impacts will only worsen as the global market for concrete continues to grow, especially in growing economies like China and India, right? The construction industry needs to become more sustainable by minimizing carbon emissions and reducing resource and energy use. Such a vision was set out in part in 2023 at the United Nations Climate Summit in Dubai through the Cement and Concrete Breakthrough Initiative, launched by 45 world leaders. This initiative aims to reduce the emissions associated with producing 1 ton of cement by around 20% by 2030. Okay, per ton, 20% reduction in emissions. Compared with the 2020 levels as the baseline, that 20% is with respect to 2020 levels of emissions per ton. Strategies include increasing the use of alternative fuels and other cement-like materials, using construction materials more efficiently, and implementing carbon capture and storage. Reducing emissions is achievable, but a more comprehensive strategy for sustainable concrete is also needed, with the ultimate goals of net zero carbon emissions and use of 100% recycled materials. So we'll look at a figure in a minute. Here we set out the key ingredients of a net zero concrete strategy. Okay, so first one, design more efficient kilns. Cement is produced by heating a blend of limestone and clay in a kiln. This process releases CO2 as limestone decomposes, and it's also energy hungry. The chemical reactions involved require temperatures as high as 1500 degrees C. Most kilns run on fossil fuels and have poor thermal insulation. So upgrading kilns can save energy and reduce carbon emissions. For example, over the past few decades, much of the world has moved away from vertical shaft kilns, which work more like a blast furnace. Material is added at the top of the column, and this is heated from below using gas or coal to eventually form the cement component of the clinker. These are being replaced by rotary kilns, which feature a horizontally inclined rotating shaft that helps move material through the kiln. Rotary kilns outperform shaft kilns in terms of production capacity, product quality, and operational flexibility, and can process 60 times more cement than the average shaft kiln. Their energy efficiency can be improved by 20 to 50% by using technologies that conserve and recover waste heat, improving insulation, and optimizing operations. Using computer modeling and real-time data can increase the efficiency of the kilns further. To make kilns even more efficient, next generation technologies are being explored. These include all-electric kilns and ones that suspend raw materials in hot air to speed up reactions. Renewable energy sources, including solar, wind, and biomass, as well as hydrogen, can be deployed, as can carbon capture and storage technologies to lower carbon emissions. Leading Chinese cement manufacturer, including Anhui Kong Cement, Chinese National Building Material, China National Building Material, and China Resource Cement have established next generation technology pilot projects. Use less clinker, right, as the product of splitting the calcium carbonate. Reducing the amount of cement clinker used in concrete can also bring down emissions, of course. Some of it can be substituted with materials that require less energy to produce, including industrial products such as fly ash from coal combustion, ground blast furnace slag from iron production, and recycled powders derived from materials such as glass, brick, and concrete, which we have discussed a little elsewhere, but it's always good to remind ourselves. However, current standards in China and Europe only allow up to 20% of the clinker in commonly used types of cement to be substituted by ash and slag. There are ways to replace more of it while maintaining performance in construction. Updating these standards to reflect ongoing technological advancements is essential to widen these options. In limestone calcined clay cement LC3, limestone calcined clay cement, half of the clinker is replaced with a type of clay and a combination of limestone and gypsum, which cuts CO2 emissions by 40% while maintaining the required physical properties. Major cement manufacturers such as the Swiss firm Holcim and Germany's Heidelberg Materials have already adopted this technology. It's used in Swiss Embassy building in New Delhi, for example. Moving forwards, it's essential to understand better the properties of various clay sources and to optimize their processing to ensure homogeneity and stability. Long-term durability studies need to be conducted across diverse environmental conditions, and large-scale trials are needed to address manufacturing challenges. Developing standards and increasing awareness among stakeholders is always crucial. We can also just use less cement, so reducing the proportion of cement paste in concrete is another strategy. Conventional concrete typically contains about 30% ordinary Portland cement paste by volume. Using less can make concrete harder to work with as it becomes stiffer, but research on optimizing the packing of concrete particles indicates that the volume of paste can be reduced to 18 to 20% while maintaining performance. Okay, can be reduced to 18 to 20%. That's a huge cut, right? The Ultra Green Concrete project, announced in 2023 and supported by the Swiss National Science Foundation, has set an ambitious target to reduce the paste content even more, to as low as around 13% by volume. This goal relies on the material having a dense particle structure known as advanced high packing and the incorporation of materials such as modern super plasticizers. Challenges to overcome include the entrenched misconception that using less paste will affect the concrete's strength, and ensuring that this close packed concrete meets practical tests including durability and workability. Advances in big data, machine learning, artificial intelligence, and so on can also play a part in designing more sustainable concrete. For example, producers mainly depend on the 28-day compressive strength benchmark specified in current standards. Through computer modeling, the researchers can identify other time points to guide concrete design. No discussion is now complete without bringing up AI and ML and so on, right? Use less conventional concrete, so you reduce cement and so on, and then also just reduce the amount of concrete. Reducing concrete consumption by extending service life, optimizing the design of structures, and using advanced construction technologies such as 3D printing offer other ways. Reducing concrete consumption by extending service life, optimizing the design of structures, and using advanced construction technologies such as 3D printing offer other ways to reduce carbon emissions and material use, concrete formulations can be tailored for specific projects to minimize the unnecessary consumption of concrete and its environmental footprint. Options include formed concrete or those including a high proportion of recycled content. Old concrete components can be reused by casting them in fresh concrete, and other materials such as the fiber reinforced polymers and steel sleeves can be incorporated to enhance structural performance while using less concrete. Although constructing a building requires a lot of energy, clever designs that lower the amount of energy needed to run it once it is built can save more. Obviously, we discussed this elsewhere, using natural light, natural circulation, and increasing well-being while also reducing energy and water use. For example, using lightweight aggregate honeycomb structures or composite materials in concrete can enhance the thermal insulation of buildings so that they can run with smaller and more efficient heating, ventilation, and air conditioning systems. Photovoltaic technology could be embedded in concrete, although many research challenges remain, including optimizing their efficiency, quality control during manufacture, degradation, environmental impacts, and end-of-use recycling. Advancing these technologies will require close collaboration between material scientists, engineers, and architects. Already happening quite a bit, but we need more. The collaborations. Sequester CO2 into concrete itself. Concrete can be engineered to absorb and store CO2 during its manufacturing and curing, as well as servicing and recycling stages. One study estimated that economically viable CO2 mineralization in concrete materials could mitigate up to 15% of CO2 emissions from cement clinker production, and theoretically almost 60% reduction is possible. The problem is that some CO2 mineralization technologies are still expensive compared with manufacture of conventional products and other carbon capture and storage methods. So people hesitate because obviously unless there is subsidy and incentives, businesses are not going to jump on more expensive methods even if they are environmentally friendlier. For example, producing a carbonated concrete block is around 35% more expensive than producing it with ordinary Portland cement at a cost of 161 euros or 166 US dollars to avoid 1 ton of carbon emissions. For now, this limits its use. Incorporating bio-based carbon-rich or carbon-negative materials such as biochar, recognized by the Intergovernmental Panel on Climate Change for its CO2 removal capabilities, into concrete can offset carbon emissions as well, although the physical and chemical properties of bio-based materials often create compatibility challenges with concrete. Artificial aggregates might be designed to address this issue. Green roofs and vertical gardens are also gaining popularity as design elements in urban landscapes, facilitating CO2 sequestration by buildings and bolstering sustainability efforts. Developing concrete that can perform artificial photosynthesis might shape the next generation of sustainable construction materials. Okay, we're getting closer. I'm reading the whole thing because it's relatively short and they're all good points, and this is a very important topic as well. Recycled concrete with a carbon footprint of near net zero, and that is based on natural resources, is an ambitious concept, but it can be realized by following these strategies across its lifetime. First, design concrete components as prefabricated modules and join them with the mechanical methods rather than permanent bonding, so that components can be separated for recycling. This approach is being used in places such as Singapore and Hong Kong, although largely to reduce labor costs rather than environmental worries. Aspects of recycling such as design for deconstruction, waste minimization, the use of recyclable materials and prefabricated components need more study and must be factored into the designs from the start. Although designing for deconstruction and recycling might decrease the cost from a life cycle perspective, it often increases upfront construction costs, and people always hesitate when you have to put up more money upfront. Secondly, to recycle concrete and so on or design, demolition techniques must be developed that preserve the integrity of structural components so that they can then be separated out instead of just blasting it and collapsing it into a big mess. Damaged components should be sorted, crushed and ground, as well as screened to segregate concrete into aggregated and powders of various sizes. This will require advancing smart crushing technologies to produce a comprehensive size of recycled aggregates with optimal packing density for reuse, right? Third, rigorous quality control of recycled materials is crucial to guarantee their safe application. Technical standards have been developed for recycled aggregate concrete in engineering projects after decades of research. For example, in 2016, we contributed to the construction of a 12-story building with a shear wall reinforced concrete frame in Shanghai, China, which incorporated 30% recycled concrete coarse aggregate. The performance of this building was demonstrated to be comparable with that of an adjacent standard building. This is a group of Chinese authors who are talking about their own work. Fourth, concrete formulations that maximize the amount of recycled materials must be developed. The ultimate aim should be fully recycled concrete using 100% recycled aggregate and 100% recycled powder derived from crushed concrete waste. Decades of research have been dedicated to recycled aggregates, but future efforts should prioritize enhancing the reactivity of inert recycled concrete powder, enabling it to effectively replace cement clinker as a binder. To advance the implementation of recycled concrete technologies, long-term monitoring, performance evaluation, research and development of specialized additives, and the establishment of comprehensive standards are essential. Over time, government support, promotion, and increased public acceptance will have crucial roles akin to the dissemination of information about the environmental issues, whereby individuals opt for eco-friendly paper bags over plastic ones, for example. I won't go into details there, but it's not that simple, but nonetheless. What about policies and practices? Achieving the vision of net zero concrete requires collaboration across the supply chain. Fostering cooperation between policymakers and industry stakeholders is also essential, along with providing education and training on the concept to ensure its successful adoption and execution. The Breakthrough Agenda report is playing a pivotal role in instigating the policy and practice transformations needed to attain net zero emissions in the cement and concrete sector by some timeline, 2050 I suspect. In the past year, some progress has been made in defining low emission cement and concrete with advances in methods to measure emissions themselves. The Global Cement and Concrete Association, in collaboration with the UN Industrial Decarbonization Initiative, worked on establishing standard definitions, while organizations such as the German Cement Association developed certification schemes. People want to have certification to be, appear sustainable or be sustainable. It's a status issue as well. However, definitive international agreements are still pending. In 2025, countries and companies should finalize definitions for low emission cement and concrete, establish international certification schemes, and refine emissions measurement standards, strengthen collaboration through forums such as the Global Cement and Concrete Association and the Industrial Decarbonization Initiative will be essential, of course. Furthermore, promoting performance-based standards will enhance material efficiency and support decarbonization efforts. Coming closer, non-zero concrete entails advancing towards not only zero carbon emissions but also reduced energy and resource consumption. Future policies and practices must reflect this holistic approach to ensure a sustainable construction industry as a whole. Okay, steps to to net zero concrete, then carbon emissions from construction industries can be slashed through a combination of producing concrete more efficiently, using less cement and its component clinker, substituting materials and recycling. This could allow net zero to be reached by 2050. Again, that's the number I mentioned before. So going from 2020 to 2050, you are looking at net carbon emissions and how, if the percentage 100, how you would reduce these or make them increasingly sustainable by using energy more efficiently and switching to renewables for production at 16%, using less clinker as 15%, using greener cement materials is these are estimates, of course, using less cement 12%, using concrete sparingly in building designs by considering recycling and reuse, which will give us 18% saving or increase sustainability by 18%. Capturing and storing CO2 in concrete, 15% sustainability addition. Adding carbon negative materials at 8%. Carbon negative is a tricky word, but basically that means you are going to somehow take out more carbon than you emitted in the first place. So that's 2050 net zero. Wow, that'll be very, very nice, considering constructions will go on. Not only new construction, but actually a lot of old buildings are coming of age or coming to the end of their life cycle, and they will be destroyed and new buildings will be built. Maybe new buildings will be more energy efficient, but or use less cement and all these good things, but in the meantime the buildings that are standing need to be recycled very intelligently, and this is a big problem for big cities as well as a lot of the industrial complexes and so on. So let's leave this here.